Alright, subscribers, welcome back to another fantastic episode of Science with Surbeck. Today what we're going to be talking about is AP Chemistry section 17.4, which deals with the solubility product constant. Now, there are three objectives I'd like you to be able to achieve by the end of this video. Objective number 1. Write the solubility product constant for a salt. Objective number 2, calculate the KSP from solubility data and solubility from the value for KSP of an insoluble salt. And then objective number 3 is calculate the effect of an added common ion on the solubility of a slightly soluble salt. So let's go ahead, let's get started with what is the solubility product constant. And so by definition, the solubility product constant is defined as the equilibrium constant for the equilibrium between an ionic solid solute and its saturated aqueous solution. Alright, so there is that written definition. Now, again, I'm a big fan of seeing this in how we would actually come across it in chemistry. So I have this example down below. Down below I have solid barium sulfate. And in this particular instance, remember we're dealing with this solubility product constant. This, again, K is what we're going to be dealing with. And so we come to equilibrium, which is a little bit odd thinking about that. But we look at, hey, how much barium or how much sulfate is dissolved in solution, and it kind of relates back to that solvation process. So we start out here with just a couple of points, and then we'll actually write the solubility product expression for this. So number 1, because barium sulfate right here is a solid, the equilibrium expression depends only on the concentration of ions. Alright, so when we write our solubility constant expression, we're just going to be looking at these aqueous ions here in solution, and that will become pretty clear when we write this expression here. The other thing is this: the equilibrium constants indicates how soluble the solid is in water. So indicating how soluble it is in water tells us how much is dissolved that relates back to that solvation process. And then to go through this example here, to actually write the solubility constant expression, we get this, and I'm going to give me some room here. So down below I'm going to put expression. I know it's squeezed into that space there, but the solubility product expression for this above equilibrium is going to be this: the KSP, which is the solubility product constant, is equal in this case to the concentration of the barium ions that are dissolved, and that is multiplied by the sulfate ions that are also dissolved. Now, don't forget when we write that equilibrium constant expression that we put these things to that power. So we do need to worry about squaring it or cubing it if we have that expressed in our equation. So now we move down to this general overall statement. And this general overall statement is this: the solubility product is equal to the constant of ions raised to powers corresponding to their stoichiometric coefficients. Alright, so that statement there is saying the same thing as we did our example up above. So now what we can do is we can actually get into more details, a little bit more depth of what solubility is, and we've talked about this before, but not related into this equilibrium constant expression for this. So we start out here with what solubility, and solubility is defined as the amount of substance that dissolves to form a saturated solution. So there's that definition of solubility. Now, this is most of the time in units of gram per liter. Now, molar solubility, very similar here, is defined as the number of moles of solute that dissolves to form a liter of saturated solution. And molar solubility is normally in the units of moles per liter. Now, I'm going to go over some steps to go from solubility to KSP and then vice versa. But before I get there, I just want to talk about the magnitude or the size of that KSP. So, a large KSP means that a lot of solid will dissolve in solution, in a saturated solution, and a smaller value, and again, I'm talking 10 to the power of negative 10 and things of that nature, a small value of KSP means that we will have less solute or not as much solute dissolve in that saturated solution. So let's go over the steps how to do this, and then we will actually go through the process in the next couple of problems here. So to go from solubility to KSP, the first step is to convert solubility into molar solubility. And this is done via molar mass. So this is, again done via that molar mass, and we've done those types of calculations before. The second step is to convert molar solubility into the molar concentration of ions at equilibrium. So we're going to have to use a little stoichiometry here on step 2. The third step is to use the equilibrium concentration of ions in the KSP expression. So that's where we're going to plug our values into that KSP expression that we've already established and solve for actually KSP. Now, if we go backwards, we start out with KSP and we want to find the solubility of an individual ion in that solution. Our first step that we do is we write the KSP expression. The second step that we do is we let X equal the molar solubility of the salt. And this X business here is really similar to what we did when we went through problems like the weak base, weak acid. It's very similar to that setup. Our third setup is use the stoichiometry of the reaction to express the concentration of each species in terms of X. So again, if we have a 2 coefficient, for example, we're going to have to put plus 2x, not just x. That's what this means here. And then our fourth step here is substitute these concentrations into the equilibrium expression and solve for x. So again, to emphasize this is real similar to how we solved the weak acid, weak base problem. And this, KSP, I didn't mention this, but KSP can be found in the back of the book in that appendix. Right on the other side of that page is where you can find the KAs. You can find the pre-designated KSPs. So the best way to do this is actually go through an example. So we start out here going from KSP to solubility, this bottom one here. And so we start with this. We have a lot of information here, and we're going to pick through this, and we're going to be able to solve our KSP. So We have solid silver chromate is added to pure water at 25 degrees Celsius, and some of the solid remains undissolved. The mixture is stirred for several days, hopefully not by hand because that would be tiresome. But anyways, this ensures that equilibrium is achieved between the undissolved silver chromate and the solution. And then afterwards, after it's stirred for several days, they find the silver ion concentration to be 1.3 times 10 to the negative fourth molar. And then we assume that silver chromate dissociates completely and there's no other equilibria involved. And so we want to know what is the KSP for the entire solid silver chromate. So again, we always want a roadmap here in chemistry, and a roadmap means what we are going to have an equilibrium expression in this case written out. So we start out here with silver chromate, and the problem said it was solid silver chromate, and this, we've talked about this a little bit in these notes, this comes to equilibrium. So now what happens here is we get our Ag1 plus ions to break out in solution, and these things are aqueous. And now we have to balance this out. So because we had Ag2 over here on the left, this means that we are going to need 2 Ag plus ions. Now, we also have these chromate ions to deal with, CrO4, again, 2 minus, and this is an aqueous solution that we have here as well. Now, what we have to do is this, or what I like to do is I like to go ahead and write my solubility constant expression right here as we go. So KSP is equal to just the ions that are dissolved in solution. So that means we do not work with this silver chromate. And so that means we have this. At KSP, we have our concentration of silver ions. But remember, we have to raise it to this stoichiometric power. So we put a 2, or we raise it to a power of 2. Now, our chromate ions, there is only a coefficient of 1, so we put those brackets to represent our concentration, and we raise it to the first power, which we don't put there, but that is our KSP expression. We're going to come back to that here in a second, but we get to this. Because I have essentially a formula, I like to list out everything that I have and solve for what I don't have. So nowhere in the problem did it say our KSP of this substance is this. So this is going to become our ultimate question mark. And then we have the concentration of Ag+. Now, the concentration of Ag+ was given in the problem to be 1.3 times 10 to the negative fourth molar. So we get 1.3 times 10 to the negative fourth molar. Now, the chromate ions are not explicitly given. It's not outright stated here, but what we can do is a little stoichiometry. So what I'm going to do is I'm going to start out with the same value that I had for Ag+, except instead of molarity, big M, I'm going to start in moles per liter. So I'm going to start out this. I don't have the concentration of chromate given, but I have 1.3 times 10 to the negative fourth moles per liter of Ag+ ions. Now what I'm going to do, we can use stoichiometry here to get rid of moles of Ag+ and end up with moles of this chromate ion. So what I end up doing here is a little stoichiometry. Again, I have moles of Ag plus, so that means moles of Ag plus must be on the bottom there to cancel out. And I want to convert to moles of my chromate ion. So I end up with this. Now, again, mole over mole, we use stoichiometry and we find this. We have a stoichiometric value of 2 for Ag plus, so we put that there. And we have a stoichiometric value of 1 for chromate. Now, all I have to do is this. All I need to do, or all I need to punch into my calculator, is 1.3 times 10 to the negative 1.3 times 10 to the negative fourth. And I'm going to divide that by 2 and multiply it by 1, but that gives us a value. I'm going to put it in scientific notation. That gives us a value of 6.5 times 10 to the negative fifth. So the value for our concentration of chromate ions is 6.5 times 10 to the negative fifth moles per liter. I'm going to express that back into molarity. So now the only thing that I have to do is this. I just have to plug these numbers, these concentrations, back into my solubility constant expression. So what I'm going to do is this. I'm going to say KSP, which we still don't know yet. That's what we're going to calculate. Our KSP is equal to the concentration of silver ions, which was given at 1.3 times 10 to the negative fourth molar. And now it's important here. We have to square this value. We multiply it by the concentration of chromate ions, and that concentration we calculated via stoichiometry to be 6.5 times 10 to the negative fifth. And now all we have to do is plug this into our calculator. So we get this. We get 1.3 times 10 to the negative fourth. Now what I always do is I go ahead and I square this value and I press enter. Then I'm going to take this answer right here and I'm going to multiply it by what we found the chromate ions to be, which was 6.5 times 10 to the negative fifth. I close those parentheses and I end up with this. My KSP, which I had 2 significant digits here given in the silver ion concentration. So I'm going to round this to 1.1 times 10 to the negative 12th. Now, if you've looked in the back of the book, that value matches out what the KSP value is for silver chromate. And I'll show you how to use that chart here in a second. Now, remember our K is unitless, so this right here becomes our final answer. All right, so we've gone through those first set of steps that I've given you. Now let's go the other way around here. So we start out with this. We are given that solubility and or we want to find the solubility from the KSP. So this problem, like I said, kind of follows that same way we did weak acid, weak base problems, but we have calcium fluoride. It dissociates completely upon dissolving, and there are no other important equilibria affecting its solubility. Great, that means, hey, it dissolves. We want to know, in grams per liter, what is the solubility of calcium fluoride? So what we have is this. We're given a KSP, which we'll get to here in just a second, but we have solid calcium fluoride. And it is dissolved onto this. We get calcium 2 plus, which is aqueous, and we get 2 F minus or fluoride ions. Now, what I'm going to do, before I write the equilibrium or the solubility expression here, what I'm going to do is I'm going to make room for my ice chart. All right. So my ice chart here, again, just giving me plenty of room. My ice chart, I'll get to here in a second. But then, again, I like to see a full roadmap. I like to see a full picture before I get started here. So my KSP is going to be equal to my calcium ions, Ca2+, the concentration there, times the fluoride ions, F minus, and it's important here, stoichiometric coefficients matter, and we're going to raise it to this particular power. Now, all I'm given in this expression right now is my KSP. I don't know these two values. So let's think about this. If I have solid calcium fluoride and I'm going to make a solution, number one, at the beginning of this, I don't have any calcium ions or fluoride ions. So our initial concentration is going to be 0. And then over time, as our calcium fluoride dissolves and it dissociates completely, so we, again, can just put a dash mark here. We don't have to worry about calcium fluoride. But as it dissociates, it's going to gain some calcium. We don't know how much calcium ions it's going to gain, so we're going to say plus X. And it's going to gain some fluoride ions. So again, we don't know how much. We put plus 2X. X represents, hey, we don't know. 2 represents that stoichiometric coefficient. So we end up with this. At equilibrium, we have X for our calcium ions, and we have 2X for our fluoride ions. Now, luckily for us, we are at equilibrium, so we can plug these values back into our expression. Now up here, we are given the KSP of 3.9 times 10 to the negative 11th for calcium fluoride. Now, if you weren't given that value for KSP and you're expected to do this type of problem, again, in page 1063 or Appendix D, we get this KSP. So I'll zoom in a little bit. This is listed in this particular book in alphabetical order, and so you scroll down to calcium fluoride, and the value for calcium fluoride is 3.9 times 10 to the negative 11th. So that's how you look up the value for KSP if you were not given it initially. All right, so now we can get down to actually calculating these values. So we end up with this. Our KSP, which was given, or I just showed you how to look it up in Appendix D of the textbook there, we get 3.9 times 10 to the negative 11th. Again, that's unitless, times the concentration of our calcium, which we found was X, times the concentration of our fluoride, which was 2X, and this whole business gets squared. So now I'm going to do a little bit of consolidating. I have 3.9 times 10 to the negative 11th equals X, which I'm going to leave, X times 2X squared. I'm going to do a little math here. 2 squared is 4. X squared is X squared. And so now I can consolidate. Now I can go through one more time. This business right here, X times 4X squared, gives me 4X cubed. still equals that KSP of 3.9 times 10 to the negative 11th. And so now all I have is a simple algebra problem. So what I'm going to do right now is I'm going to get rid of this 4. And so in my calculator, I'm going to punch in 3.9 times 10 to the negative 11th divided by 4 equals 9.75. 9.75 times 10 to the negative 12th equals my x cubed. Now, to get rid of your cube, and we got to make sure we punch it into the calculator, but we're going to take the third root to get rid of that x cubed. Each side needs to be able to calculate or get rid of the cube factor by taking the cubed root. So what we are going to do is this. In our calculators, we take 3 and then we punch in to the third root of this 9.75 times 10 to the negative 12th. And so what we get is a value, and I'm going to round down to 2.1. We get 2.1 times 10 to the negative 4th to equal x. Now, what we have is this. 2.1 times 10 to the negative 4th equals x. Well, x is just our calcium, Ca2 plus ions. So what I am going to do is this. I'm going to grab another sheet of paper, and we're going to talk about what x actually is, and we are going to be able to do some calculations. All right, so it's important to listen to this. So we found x to be 2.1 times 10 to the negative 4th, and that is a calcium 2 plus ions. That's what at equilibrium that x means. Now, because calcium 2 plus and calcium fluoride have a 1-to-1 stoichiometric ratio, what we can say is that this value for x that we found is actually, and this is where I'm going to use this other sheet of paper, is actually 2.1 times 10 to the negative 4th moles per 1 liter, so molarity, of calcium fluoride, CaF2. Now, the problem said, what is my solubility in grams per liter? So because we are dealing with calcium fluoride, what we are going to do is this. We don't want it in moles per liter. We want it in grams per liter. So what we do is instead of having moles, we cancel out moles of calcium fluoride, and on top, we put grams of calcium fluoride. So when we do this, all we have to do is find out the molar mass of calcium fluoride. So if you look on the periodic table, calcium has a molar mass of 40.08. So 40.08 plus the mass of fluoride, which I'm going to put this in parentheses. The mass of fluoride is 19.00 times 2 because we have 2 of them. So the molar mass here for calcium fluoride is 78.08 grams per 1 mole. Now, when we do this calculation, so we take 2.1 times 10 to the negative 4th, and we multiply it by 78.08, we get this value, and I'm going to put it in scientific notation. We get 1.6 times 10 to the negative 2nd grams per liters. So 1.6 1.6 times 10 to the negative second grams per liters is the solubility of calcium fluoride. And this ultimately becomes our final answer. All right, so there was a lot discussed in this particular section, a little bit way of dealing with it. But hope you've learned a lot. Hope you can take something away from this. And as always, remember to subscribe.